Hi. Welcome to your Wednesday show for Life Sciences. I am Looney. That is Cheryl.
I'm very disappointed.
Why?
What happened to the hello?
No, it comes and it
I
goes.
see it goes today.
It comes and it goes. Depending how my voice feels, you know. So
obviously not a good voice day today.
No singing for me.
No singing.
Yeah, but how are you?
I'm well, and you?
I'm good, thanks. What are we doing for the grade 10s today?
Grade 10s, we are doing the last in our skeleton, our support system. We're going to look at what the structure of a bone is and the joints and how all of that put together which brings about movement.
All right, guys, we are doing bones and joints. I hope you guys are excited for the show. Remember to hit us up on Facebook on facebook.com/LearnExtra, and then on Twitter, our handle is @LearnExtra, and then you can get all the show notes, the videos, and the schedules on learn.mindset.co.za. And just a quick thing, guys, if you see that we haven't posted the challenge question or any image-related posts on our Facebook page, please just bear with us. Facebook is having a bit of a problem with posting pictures, but Cheryl will help you with the challenge question and show you what you need to know and all of that stuff. And remember, if you want to win this awesome Casio calculator, all you need to do is enter the Test Yourself competition, and the link will be posted on our Facebook page under the post link. So you will see that there's view, there's download, then there's Test Yourself. That is the link to the entry form to stand a chance to win this awesome Casio calculator. So with that said, Cheryl.
So you can now rest your voice.
Yes.
Welcome, grade 10s. This is the last in our series of the skeletal system. And as I said to you, those of you who watched last week, I find it's a bit difficult for me. I like to start off with the structure of the bone and then go into the skeleton, all right? But obviously your syllabus is a little bit more rigid than that. So what we're going to look at today, and we're going to go over there just now, you'll see we're going to have a look at the structure of a long bone, right? So we're actually going to look at the structure of bone. And then we're going to join everything together. And that was a bit of a pun, all right, because we're going to be looking at joints. Right? How bones, thank you. I didn't even have to ask you to go on cue. All right, and we're going to look at joints to see how bones, all right, fit together and the kind of movement they enable us. And then we're also going to look at muscle. Okay, we looked at all of these when we looked at our mammalian tissue, and we're going to see how we put all of this together and we bring about movement. And then just briefly look at a few of the things. Sometimes things don't always work out quite well in our skeletal system, and there are a few skeletal disorders. Okay, when we start off with bone, and that was like, I felt like a Ferrari over there. Okay, the challenge question. I always forget the challenge question one of these days. Okay. The challenge question, and for those of you that don't have the image on Facebook, I think John is trying to enable you to describe the different muscles. It is, you need to look carefully, all right? And it's one of those questions that you need to actually do the action yourself so that you're able to work out which muscle contracts and which muscle relaxes. Okay, the diagram shows some bones and muscles in the leg of a human, all right? So there you'll see you've got, let me get my pens, come pink, all right. We've got Y, muscle Y, okay, that's the bones, not the bones, the muscle of what we call, all right, the thigh or your quadriceps. Number X is generally known as your hamstrings, and number Z is going to be your joint. And there are various options. I need to sneeze, but I won't. I will just try and hold it in. All right, muscle Y. Now you need to tell me what happens at muscle Y, all right, and what happens at the leg at joint Z. So you got 4 options. You need to see when muscle Y does this, what does the joint do? And you need to be able to match the muscle action with the joint action. Okay, I don't want to give too much away. The diagram in front over here should be a familiar diagram to you, all right? Because when we started with mammalian tissue, obviously one of the tissues that we looked at was bone. So the very first here, when I'll show you these diagram of the Haversian systems, all right, of the bone that's made up in these concentric circles, lamella, right, with the osteocytes, they should be familiar to you. So we know the structure of bone, okay? That is the microscopic structure. Now when we look at what the bone, the macroscopic, the large structure of the bone, we're going to look at what we call the structure of a long bone, okay? I'm going to put this diagram up on the board for you, but I'm now going to go across because we're actually going to look at the structure of the long bone. Right, for those of you I'm going to obviously be using one that I got at our butcher, okay? But you guys, you can do it with a chicken bone. A chicken wing has got all of the mammalian tissue. And those of you, when you order the drumstick, all right, that is what you're looking at. You're going to look at the long bone. But I'm going to go across here. Our cameras are not movable today because most of our cameramen are out on a shoot. So I want to be able to explain to you. Okay, if we have a look over here, we're looking at the structure of a long bone. All right, this is the outside portion. And the reason that it's called a long bone, that sounds rather stupid, and I'm going to put this one here, is because it's long. All right? It's long. So when we talk about a long bone, we are talking about your humerus, we're talking about your ulna, your radius, your femur, your fibula, and your tibia. Now, when we look at the structure of the long bone, there's two things that are very apparent. Number one, here is this round portion at the end. If I show this bone in front of you over there, all right, you will see, have a look, we have this large round portion at the end. And then we have this long portion going from that. Have a look here. All right, so we've got round over here, we've got this round portion, and then we've got this long portion. Okay, they are called, this is the head, but we refer to it as the epiphysis. The epiphysis is the round. This long portion from here to here is the shaft. That is called the diaphysis. Okay, so we have the head and we have the shaft. Now, if we have a look at the head, all right, if we look on the outside, we're going to see, and as I said, next time play around with your chicken bone. You're going to see this white, all right, shiny, smooth tissue that is going to be your hyaline cartilage. Now remember, as I said to you, bones are going to join to other bones. So when they move across each other, you want the movement to be smooth. So we have this articulating cartilage on the outside, at the ends of our heads, of our epiphysis. If you see here, this side's not as clear because we've got a lot of muscle attachment there. Because a lot of the muscles attach, all right, their origin is at the heads of the bones. Now if I turn it inwards, right, now we see something totally different. Okay? When we look at bone, we are going to notice the following. If I move this one, there we go. We are going to see different types of bone in our long bone. Now, this over here is the shaft, as I said, and this is made up of compact bone. In other words, the bone, the osteons, are very, very, very close together. It's very, very hard. And we would want that because our shaft, that's where all our weight, all right? That's our weight-bearing part of the bone, okay? So the bone here is much stronger. At the ends, in our heads, we have spongy bone. Now I'm going to bring this one a little bit closer because you can see, look at all the holes, all right? Look at all the holes. We can see spongy bone much clearer, all right, over there. It's far more porous. It's almost, as I said, it's got far more holes in it, and it's not as, all right, strong as my compact bone, okay? Then if you look carefully over here, you will see that there is a very visible line, okay? That is called the epiphyseal plate. And it's in this section over here that you're going to have cells that are able to divide by mitosis, all right, enabling bone to grow. So in other words, all right, this is your growth plate. So when you grow in length, the cells divide in this region, causing the bones to elongate. Okay, now the inside of the bone. And if I can slowly, let me use this over here. You can see I can start, all right, to clear all of that out. Okay, it's not actually hollow. What I am clearing out now, all right, and if you can remember when we looked at the skeleton, one of the functions of bone is to produce blood cells, all right? And what I'm actually clearing now, all right, is bone marrow. Okay, all of that, we can hollow it out, and as you can see over there, all right, all of that coming out is bone marrow. And that bone marrow is obviously responsible for the production of our red and our white blood cells, specifically our white blood cells here and our red blood cells in the head. Okay, so what you need to remember: epiphysis, head; diaphysis, shaft, right? Epiphyseal plate, this is the bone marrow cavity. Now we can't see it, right? But surrounding, if I were to scratch on it, there's a layer of connective tissue surrounding the bone, and that is called the periosteum. Os meaning bone. All right. So and on the outside over here, this nice white smooth, that is the hyaline cartilage, the articulating cartilage. You can't see it too clearly, but I'm going to, let me get into view. This little piece over here is what's left of a ligament, because a ligament is going to join another bone to each other. Okay, now we're going to go across. Let me just wipe my hands on my jeans, and my mother's going to have a fit. All right. Okay, guys, so if we have a look at the structure of the long bone, right, we're having a look. There's the epiphysis, the head; the diaphysis, the shaft, right, compact bone in the shaft; spongy bone in the head; the bone marrow in the middle. Okay. Now, when we look at bones, you know, as biologists, we love to classify things, but this is actually quite nice and easy, right? When we look at the skeleton, and I'm going to quickly bring two of them across here, all right? When we look at the skeleton, we notice that they classify the bones according to the different shape, all right? So we've just looked at a long bone, all right? So there are long bones. What's a long bone? It's got compact bone on the outside, all right, in the diaphysis, and spongy bone at the heads. Now, I don't have an example here, but there are, all right, short bones. And short bones look exactly like long bones, right, on the outside, except, yes, you guessed it, all right, they are much shorter. So let's have a look here. So when we're talking about the short bones, right, over here, there we go. Oh, I don't even need a pen. The short bones over there, all right, can be some of the carpals of our wrist, but also the metacarpals of our hand, all right, and what mirrors our hand? Our foot, right? The arch of our foot, the bones of the arch of our foot, our metatarsals, they are also going to be short bones. Okay, then we've got flat bones, and the flat bones, obviously, they like the shape. If you can look at it, you can quite easily see which shape it is. Over here, the flat bones, those are the bones of the skull. You need them to be flat because they need to form this round protective barrier, all right, around your brain. The sternum is also a flat bone. Then you get those that don't fit into any category, all right, and it's quite simple. We just call them irregular bones. And over here, you'll see, here are a few vertebrae, okay? Don't have a particular shape, long, short, all right, or flat. They have all little funny processes going out of them. Okay, now there's a whole lot of writing here, but basically, when it comes to bones join with other bones, okay? It's as simple as that. Because we need to bring about movement, we need to bring about protection. And if you've listened, all right, over the last couple of weeks, quite simply, the joints, certain joints allow some movement, some joints don't allow any movement, and we're going to look at a type of joint today which allows free movement. Okay, so when we look at joints that can't move, we're looking at the sutures. Remember when we looked at the skull? Oh, there's the pen. Right, when we looked at our skull, often we see it looks like these stitches, because remember, it's made up of a few bones that are joined together, and they are called fibrous joints. And fibrous joints, all right, I want to keep this because we'll use it. Fibrous joints don't want any movement. It protects the brain, all right? You don't want the brain, all right, things to be able to move around. You want a solid structure that is there for protection, okay? Then we go on to joints that allow some movement. All right, let's have a look here. There's the vertebral column. In between the bones, because they are joined, this vertebra is joined to that one. What do we find? Intervertebral discs. Okay, not only does it help with shock absorption, but because the bones are not joined fully, it does allow some movement. The same as the ribs. The ribs do not attach directly to the sternum. If you can remember last week, again, we had the sternum, all right, and then we had the ribs, and the ribs ended. They didn't join with the sternum, because if the bones joined directly to the sternum, we wouldn't be able to breathe in and breathe out. So what did we have? This costal cartilage, or articulating cartilage. So the bone didn't attach directly, the cartilage attached. So that allowed our rib cage, right, to expand, all right, and contract when we breathe, enabling our lungs to fill up. Okay, the pubic symphysis as well. Remember, the pelvis is made up of two bones, right, and they need to be joined, right, and the pubic symphysis joins that up. Are we having a break?
Yeah.
Because I don't know if it's in or not.
No, it is in,
Is it
actually.
in?
It's behaving.
Sure, it's behaving. I want to go and wash my hands. I just smell bone. Ugh.
All right. Mindset is we are going to take a break. Before we do, congratulations to Takhatso Sebapu. You have won yourself this awesome calcium calculator. Takhatso Sebapu, congratulations to you. I hope you're excited for your new calculator. And with that said, Mindset is let's take a very quick break and I'll see you straight after this. Welcome back, guys, from that break.
Oh, is that it?
Yes.
I'm usually
I don't want
used
to
you
waste
like
your time.
Okay, awesome.
Yes.
Welcome back, grade 10s. Hands are nice and washed. Don't smell so much anymore. Okay, we were looking at the different kinds of joints, and we classified them according to the amount of movement they permitted. So my fibrous joints, no movement. My cartilaginous joints, a little bit of movement. And now for the first time you're going to hear the word synovial joint. All right? A synovial joint. A synovial joint in here. All right? Synovial joints, they are the joints that are far more movable than obviously the other two that we have looked at. Okay, first thing you need to know, very important. Oops, we went one too fast. This is the structure of a synovial joint. Okay? When we look at a synovial joint, one of the things that we must realize, okay, is it is able to move freely. All right? If I move my arms around like that, if I move my thumbs, right? If I move my fingers and my arms, they allow far more movement. Okay? Because obviously, not so much protection, but for movement, flexibility, able to do things. Okay? So how are they different? Well, a synovial joint, okay, first thing, we need to have our two bones that we have got, all right? And two bones, we need to make sure that they are stable. We are going to have a ligament in between the two bones. Okay, there's your ligament. Because that's what joins bone to bone. Ligament joins bone to bone, right, as opposed to a tendon, which is going to join muscle. Let me start that way. Muscle to bone. Okay? So it's a different thing. Now what we have is, because there's going to be a lot more movement, we need to make sure that the movement occurs as easily and as smoothly as possible. All right? So what do I have? I showed you when we looked at it just now. Sorry, it went a bit haywire. We have hyaline cartilage, articulating cartilage on each of the heads of our bones. Right? Remember, it's there when bones move across each other and they rub against each other. You want the movement to be smooth. As soon as it's not smooth, as soon as that cartilage is not there, we're going to see that could cause problems, all right, later on. Now, a double thing. The movement, all right, in order for the movement to be nice and fluid, let me use a different color because it's already there in blue. You need to have a liquid. The yellow is the liquid, right? So inside here, you actually have this watery liquid. Okay, so now you've got the articulating cartilage and you've got fluid. So the whole joint, all right, is lubricated. Remember, what do we want? Nice, easy, free movement. So here we have the synovial fluid. Now, if we've got water, all right, and that is called, obviously, now sorry, I jumped the gun there. That is called the synovial fluid. It's the fluid inside the synovial joints. Now, the fluid can't just run all over freely. You need to, all right, encapsulate that fluid within the joint. And you will see you have a synovial membrane, right, surrounding all the fluid, keeping it on the inside, all right, so that you've got all the fluid staying in. You don't want it to leak out. Some people, if they have an injury, you'll see it's referred to as water on the knee. What will happen if maybe some bone chipments get in here, then what's the knee going to do? It's going to produce more and more synovial fluid to try and make that movement easier. And the membrane is going to swell, okay, and that is going to cause discomfort and it's going to cause pain. Okay, so when we look at the synovial joints are able to move freely. And then you need to be able to draw, possibly, and label, right, the structure of the synovial joint. And if you can see over here, this is called, right, what we call an annotated diagram. I love them. I think that's how you should study. Here, you've got the diagram, you've got the labels, and next to it, you've got all the different functions. To me, that's how you should be studying life science, okay? A picture in front of you, you've got the different labels, but you also need to know the functions. Okay, but we are not finished yet with the classification. We have got different kinds of synovial joints that allow certain amounts of movement, and we're going to just look at 4 of them. Okay, 2 I've got examples here, the other 2 I'm just going to use myself as the example. Now remember, you need to now link this all up to the skeleton that we looked at last week. What did we look at first? We looked at the skeletal system. You know all the bones, so now when we look at the joints, you should be able to have a picture in your mind. All right, oopsie daisy, that was close. Our first joint, right, is called a ball and socket joint. And as I said, very often, the name of the joint actually is going to tell you exactly, all right, what the structure looks like. If we have a look over here at our hip, now remember, very often, our hip is often mirrored by our shoulder. All right, so here we have a hip bone. In our hip bone, all right, we have a capsule like this. And in that capsule, a ball fits, ball and socket. So the head of the bone fits into, all right, the capsule, and you are allowed this movement. Now when we look, so ball and socket joint, okay? Socket, ball, fits into each other, all right? And obviously the hip, what is another example? The shoulder. The head of the humerus fits into, all right, the scapula or the clavicle, the scapula. The scapula, all right, also has a socket in which the head of the humerus is going to fit in. But if you have a look, just carefully, the hip is much deeper, all right? The hip is much deeper than the shoulder. Why? Do you know why? No? Are you concentrating? Don't worry.
I am listening to you, but I don't know why.
All right. What do we want? Shoulder, we don't want it so deep, because what do we want? Flexibility.
Okay.
The hip, we want it deeper, because we want stability. All right. So even though they are the same joints, slightly different, because we want more movement in our arms, but we want our hips to be far more stable. Okay. First one, ball and socket joint. Second one is the hinge joint. and maybe just looking at the bones, you should be able to see a hinge joint, like the hinge, all right, of a door, can only flex and extend, all right? Extend, flex, extend, flex. Look at my leg, extend, flex, flex. All right, so you should have by now, oh, we went too far up. What am I missing? There we go. There's my hinge joint. My hinge joint, so lots of people say, but I can turn my arm like that. No, that's not your elbow that's doing it. It's here. You're doing it here by your ball and socket joint. My arm, there, and back. My leg, flex, and extend. All right, and you're going to see a lot of this when the World Cup soccer starts soon, hey? All right, so there we go. Hinge, like a hinge of a door. I can open and I can close a door. So let's mirror. If I have my elbow as an example of one, what's the corresponding on the bottom half is going to be my knee. Okay, next one is a pivot. All right, is a pivot. My skull with my very first vertebra. Let me put that down. Okay. What do I need my skull to be able to do? Needs to be able to rotate. I need to be able to move my head because that's how I perceive danger. And I can, if my head's like this, right, can't see anything. So my skull, all right, on my very first vertebra needs to be able to pivot. So pivot, all right, it's almost like a ballerina doing a turn. I need to turn around. And that's exactly what I'm doing when I do this. That's the pivot. The last joint is a little bit difficult, all right, I won't say to explain, but it's a very difficult image to try and I want to say explain, to show. It's gliding, all right? It's gliding. And it happens with our carpals, right? Our wrist bones and our ankle bones. When we move them, when I move my wrist like that, it actually looks like a hinge, but it isn't, all right? Because all the bones are in different positions. So when I move, they glide and slide over each other, right? Even when I do this, it looks like a hinge joint, but it's not. The bones slide and they glide over each other. Okay, so if I use the carpals of my hand, then the same would be the tarsals of my ankles. The same gliding movement would then occur. Okay, right, onto this diagram. I would suggest when it comes to how the muscle moves, I have put, those of you who've got the notes, I have put a link there. I think it's called the sliding muscle, sliding filament theory, all right? And it's an animation that shows quite simply how muscles work to bring about movement. Okay, now one of the structures of the skeletal system, although it's there for protection, is so that muscles can attach to them. Because bones, they cannot do anything. They are this dead weight. Remember, they're not tissue, but they're unable to move. But they form part, right, of our system that enables us to move. Muscles are going to be the doers. They're going to attach to the bones, all right, and they're going to do the work. The joints are going to also help, and in doing so, the muscles are going to bring about movement of the bones. So we need to have a look at the structure of a muscle. It is a bit of a challenging concept, all right, but basically we need to break it down into small little groups. Okay, a muscle can do one thing. It can contract and it can relax. It's as simple as that. The movement is quite simple. It moves in and it moves out. It moves in, and when it moves in, it shortens. And that shortening, all right, imagine when I flex my bicep, what happens here? This is where my bicep starts, origin. That's where it inserts. So if I pull, try this with your chicken wing, you'll have great fun at the supper table. All right, pull this, and when the muscle pulls, it shortens. So what's it going to do? It's going to move my arm. Right, that is how I'm going to bring movement. If I put my head down and I want to lift my head up, what happens? The muscles at the back of my head, they contract, and when they shorten, what do? They pull my head up. Okay, so muscles are going to be the movers, but they need to be attached to bone to bring about the movement. Okay, let's have a look. All right, this is the large muscle structure, okay? This over here, let me go back to my pink. All right, that is, say, for example, the whole bicep. Well, everybody knows what the bicep is. The boys like to flex it. Now, remember what I said? Muscle joins to a bone by a tendon. Now, if you can see, we start dividing it into different little groups. Okay, so we take one little group, and that is called a fascicle. So here's a fascicle, here's a fascicle, here's a fascicle, here, here, and all of those fascicles together make up what we call a muscle. All right? Now we take this one little fascicle, and as you can see, it's made up of all of these little circles. All right. Now, one of those, one little circle looks like that. It's got lots of nuclei, and we also notice that it has got striations. There are certain spots that are darker, there's my nuclei, than the other. Right, and we did this when we did mammalian tissue. It is skeletal muscle or striated muscle. That one little, all right, that is the muscle fiber. That long tube is one muscle cell, right? One muscle cell. Remember when we looked at the beginning, we said cells are going to have different shapes depending on their function. This muscle cell is long because what does it need to do? It needs to contract and it needs to relax. So when we look at it over here, let's go a little bit deeper. Okay, it's all these Z lines, M lines. I want you to concentrate on this diagram. Okay, here is my muscle. That is the one cell. Now, if we have a look, if we have a look at this one cell, we're going to notice again, it's made up of a whole lot of little tubular fibers. Now, if you have a look at the diagrams, you're going to notice there's thick parts, and there's thin parts. The thick parts, let me draw my muscle here. The thick parts, a thin part, a thick part, a thin part. All right. And that is what is going to bring striated muscle. Okay, so now if we have a look at this, do you notice it looks like this? It's got like a little oar at the top, right? And that's exactly what it does. When we have a look, let me just quickly take that away so that you can see it a little bit easier. Okay, if you have a look here, oh, pen again, multitasking, green. All right, if you have a look at these little bridges, all right, they oars. So when a muscle contracts, imagine these are my oars. They do this. They pull, they pull, they pull. And as they pull, what does the muscle do? Gets closer to each other. And then when the muscle's finished doing, they relax. When the muscle needs to do the work, pull, pull, pull. They pull across. And that is how the muscle, right, then from here, it contracts and it relaxes. It's called the sliding filament theory. Please, as I said, go and have a look at the links. Go and look on YouTube. It's a nice little animation where you're able to see the sliding filament theory. If we can finish now, or otherwise, because I'm going to go into questions next. But I'm not. We can finish quickly. Sorry.
Okay.
Okay. If we have a look at the next one, and this is related to our challenge question, right? We have what is called antagonistic muscles. All right, what does antagonistic mean? Opposite. All right, so rather than showing you a picture, let's do a simple thing. Okay, I'm going to pull my bicep. Look how strong I am. Yay. All right, Now, so what happens over here? My bicep contracts and I flex. Now, am I going to go and walk around like this for the rest of my life? No, I don't think so, because I'm going to look like a bit of an idiot. All right? So after I've proven, oh, yay, this is how strong I am, what do I need to do? I need to do the opposite. I need to flex it again. All right? So one muscle flexes, another muscle extends. Flexion and extension are opposite movements. So my bicep flexes, my tricep extends. Think about your challenge question, all right? So if I was to bend my knee, what does this one do? That extends, all right? What is this one doing to bend it up? It contracts. This is my quad, this is my hamstring, all right? Now I need to kick the ball. Soccer World Cup's coming. Here we go. I need to kick. What does this muscle do? It contracts, my leg extends, this one relax. They do opposite movement. Antagonistic means opposite.
Oh,
Drama.
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 What drama?
I don't know. I'm full of like, oh.
Okay. Mindsetters, we are going to take a break. Just a quick reminder, guys, if we don't get through any of your questions, we do have so many help desks. We've got a Facebook app for questions that you can send your questions through there. We've got our website, and then you have a Mixit app as well. So please send your questions through there. And remember, guys, the Life Sciences Learn Extra Help Desk is proudly brought to you by Axel. So with that said, let's take a very quick break, and I'll see you straight after this. Hi guys, welcome back.
Must I carry on? Or are you going to ask me that question?
Do you want me to? Because do you want me to
Yes,
ask you
let's
first
ask
the questions?
Because I want to see
Okay.
how you pronounce this word, and so does Belinda. So let's go
No,
and see.
no, please don't.
Come on.
Please don't do anything in my ear. What are the little circles in the facilis called?
Okay. If you have a look over here, a facilis is plural for the little fascicles. So if we have a look here, one little circle is the muscle fiber, all right? And that is what it's called, a muscle fiber. The muscle fiber is then made up of a myofibril, and the myofibril is made up of these little compartments called the sarcomere.
Okay, that was from Hoputso Noltando.
Okay.
And then another one from
Yes.
Hoputso Noltando. What is the function of marrow cavity?
Okay, bone marrow, all right, those are your stem cells. Bone marrow is able to divide by mitosis, and it gives rise to blood cells. All right, so if you have leukemia, right, a cancer like that, you can have a bone marrow transplant because your bone marrow makes white blood cells. And if you have leukemia, you have cancer that is eating the bone marrow.
Right. And then this one, can't see
That's
this
quite
name.
a thing. What's this? All right.
No, like
Is
when
it a
I
new
just
thing? Oh,
no.
okay.
Can
Alright.
can we not?
Just checking.
Okay, thanks. Bye. This person's name on Facebook: Science Nerd King More something. Okay, what is the type of joint between patella and femur?
Okay, the patella is not a joint, right? Remember, those of you who watched last week, the patella is a sesamoid bone. It's the only bone in the body that doesn't join to another bone. It's embedded, right, in the tendon. So the femur has a joint with the tibia, your table, and that is a hinge joint. The femur and the tibia, all right, they have a joint, not your patella. Patella doesn't join with any bone in the body. The sesamoid, only bone that doesn't.
Okay. And then one last one from Karabo Maboka. Compare the biceps and tricep muscles with respect to point of origin, point of insertion, and function.
Shoo.
No, you need to do this
Phew,
kid's homework,
okay.
okay?
It's homework, making me work for. All right, here we go. The Karabo.
Yes.
Okay, right. Look at the name, biceps, 2. What do we mean by 2? Not 2 muscles, 2 heads. All right. So the bicep muscle, okay, we have over here. It starts off, all right, one on the head of the humerus, all right, and the other one on the back of the humerus. Okay, so that is its origin. So the biceps, 2 heads. Biceps means 2 heads. Triceps then means 3 heads. All right, where does it insert? Here. All right, if we have a look, where is that bone going to? Our pinky, not to our thumb. So that is going to be our ulna. Right, where does our tricep? To our radius. Okay, what does, and there we go, what does the bicep do? The bicep, all right, causes flexion. Ooh, sorry, that was a, oof, F. And what does our tricep do? Extension. How was that? Okay.
Is that?
That's it. Yeah.
And
Very
triceps,
simple.
biceps and triceps.
There we go. Biceps, triceps,
Okay.
biceps, triceps, biceps,
Thanks.
triceps.
Thank you.
Okay, sharp. Okay, now we're going to just do this quickly, right? But sometimes, as I see to you in the skeletal system, certain things can go wrong. Musculoskeletal diseases, and I'm sure you would have dealt with it when we looked at biochemistry. The first one is rickets, right? When the body doesn't have enough calcium or doesn't have enough vitamin D and the bones are soft. And remember, what are the legs? They're your weight bearing. So if they're soft and you put weight on them, right, what's going to happen? They're not going to form very well. Okay, that's example of rickets. Then just 2 differentiations over here, right? This is arthritis. Okay, and so is this. Okay, they're both, but you get 2 different forms. This one is osteo. Osteoarthritis is usually what develops with old age. Okay, here the joints, the cartilage starts to disappear, it degenerates, and the bones rub against each other, causing the swellings, all right, and causing pain. Okay, so usually, as I said, generally tends to be an old age disease. The younger people can get it, all right. The next one is called rheumatoid. Oops, there, now we just went there. Rheumatoid. Now, if you have a notice over here, rheumatoid arthritis, even though the hands of this lady, you can see she's elderly, all right, the bones totally misform. Here, slight swelling of the joints still can, all right, manage. Here, the joints totally misform. And it's what we call an autoimmune disease. And an autoimmune disease is when the body itself attacks the body. So it's not old age that's wearing away at the cartilage and at the ligaments. The body's own immune system, all right, is wearing away. And what generally happens, what can happen to get to such a stage where the bones actually fuse. They should be a joint, but they actually fuse. And in fusing, obviously going to cause, right, that misshapenness. Then us ladies, we have to be very careful. Osteoporosis, we need to have as much calcium, magnesium, and vitamin D while we are younger, so our bones can store the calcium so that when we do get older, we don't lose it to osteoporosis. Okay, now going on to our, okay, why can't I not find where I want to go to? Because I changed the slide. Okay, questions relating. There are a variety of questions. If you have a look now you can combine, all right? If I combine this man over here, I can ask you questions on bones of the skeleton. I can ask you on muscles, antagonistic muscles, and I can ask you on joints, right? So we combine all of our sections together and we can bring up the questions. Let's have a look here. The diagram below shows the legs of an athlete while he's waiting for a race to start. The letters A to F show some muscles as well as joints that will be used during the race. Okay, when the starter's gun is fired, the athlete's right leg will straighten, pushing the athlete upwards and forwards. Which of the letters A to F indicate muscles that will relax? Okay. He's standing like this. This is the right leg. and he's going to stand up. So when he stands up, what muscle contracts? This one, all right? Because this one is the one that's keeping him down. So he needs to, or am I incorrect? All right, let's have a look on your marks. All right, if you go down like this is contracted, this is relaxed. When I stand, how do I straighten my leg? Yes, over here, this muscle is going to contract, and this muscle is going to relax. So, and don't be shy in the exams to do it. I don't know why it says a 3 here. Should just be 1. Okay, so what relaxes? Relaxes, we are going to have number C, right? And contract, we're going to have number, let's see, which one was it? Number B. All right, so relax, number C, contract, oopsie, number B. We're not finished. Have a look over here. All right, when you're going down and you get up, right, you strengthen like this. Think about here, your calf, right, your calf muscle. If you almost as if you're standing on toes, getting ready, what's going to contract? E is going to contract, it's your calf getting ready, and F is going to relax. Remember, they are antagonistic muscles. They cannot do the same thing at the same time. So if the one is contracted, the other one must relax, and vice versa. Okay, I just want to show you the different things. Okay, here, what have we got? You need to show, where's a hinge joint? Let's go back to the diagram. Hinge, all right, and ball and socket. Ball and socket, number A, the femur fits into, all right, the hip, and where is my hinge joint? Number D, my knee is my hinge joint. Right, you see all of them coming together. Right, during the race, the athlete suffered injury to his right knee, resulting in torn ligaments. As a result, he was not allowed to participate in competition for 6 weeks. During this time, he was only paid 1/3 of his monthly income. What are ligaments? They're connective tissue. All right, and what do? Join bone to bone. Okay, now, this is a nice question. All right, do you think that athletes who are unable to take part in competitions due to injury should be entitled to their full income? It's your opinion. Yes or no? Right, just make sure you have the right question. Do I have to go over the challenge question, hey, before we end? All right, guys, have a look here. All right, go and have a look on the notes at the different questions. Here, again, showing you bones, asking you which one is broken. Okay, again. Okay, older woman, an osteoporosis question. All right, if we have a look at the next one, it's a synovial joint. It's asking you again what kind of diagram. There we go. We can see that it is the hip joint. Okay, and again, asking questions on that. Let's go to our challenge question. Right, what happens to the muscle at Y, at the leg, when joint, and muscle at the leg, all right, and here, when muscle X contracts. Okay, muscle X, my hamstring, contracts. When it contracts, what happens to this one? This one relaxes, so we must look for a relax. Okay, so our two options are this. Okay, what happened to my knee when I did this? My leg bent. There we go. Number C is your correct answer. Ta-da! Is that it?
Can I ask you a question very
Yes, you
quickly?
can, quickly.
Cody Myers is asking, if your cartilage gets thinner, as in damaged, can that chip your bones if they rub together?
Yes, very much so.
All right.
Yes, yeah, definitely. Okay, is that it? Oh, you
Yes.
finished? Say something. I'm standing here.
I'm winking at you.
I'm
I'm
winking.
smiling.
Okay, we are finished for today. Please stand by to wait for Llewellyn. All right. And if any of you would like to comment on Looney's new hairstyle, please be free because it will change next week.
Oh my word. Guys, thank you so much for tuning in. She doesn't get me by now. I was
No,
winking
don't
at her.
get
I'm like, I'm winking, but she's not getting me.
But
Wow. Thank you so much, guys, for tuning in. Until next time, we'll see you then. Goodbye.